So first we will start with the problem which was covered in the theory class, and later on you can work on the problem which is not covered. Okay. So I think this is the problem which was covered, isn't it? यही वाला है everybody? Yes.
Yes,
Can you
sir.
see this?
Yes, sir.
Yes, sir.
Okay. So here you see this is a truss problem, and here you can see like there are four nodes, 1 2 3 4, and the distances are given to you, and the cross section areas are also given to you. Okay. The lengths are also given to you, and I think you might have solved this problem, and today we are going to see how the same problem can be solved in the SAP. Okay. So let me start the SAP. Okay. So is this visible to you now, SAP? Yes.
No,
Hello?
sir.
No, sir.
Not visible.
So the screen is black.
Screen is black. Okay. I thought so. That's why I asked. Uh, Let me share it one more time. Now, is it visible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. So let us quickly let us quickly see how to solve this problem using the SAP. So if you see the problem, it has got nodes which are spread over a distance of 4 meter in the x-axis, and at 3 meters in the y-axis. So we will be needing a grid of 4 meters in x-axis and 3 meters in the y-axis. Okay, so not exactly y-axis, it will be in z-axis. So let me create a new file. So in the x direction, I need only one grid space at a distance of 4 meters, and in the z direction, I need only one grid space at a distance of say 3 meters. Y direction, I don't need grid space. So as far as spacing is concerned, spacing is not at all required. And you can see the distances are there in kilonewtons and meters. So if I say okay, okay, this should be 1 because this is spacing. So if you see this, so now you'll find there is a grid space. So this distance is 4 meters and the vertical distance is now 3 meters. So let me change the view to XZ view, just like similar to the previous one. So now we have to draw the grid, okay, or the truss part. Okay, so let me quickly first of all define the parameters. So if you see the problem statement,
सर
yes,
सर एक बार फिर से स्टार्टिंग से दिखाइए सर, वो ग्रिड का क्या नाम दिया वो दिखा नहीं है, नंबर दिया वो दिखा नहीं है.
sorry,
So the number of grid spaces you have given in x, y and z direction, it is not visible. So
it is
can you
not
please start
visible.
again? Yes, sir.
Okay, I'll try it one more time. Okay, I think I will share the entire screen. That will be better
No, sir,
because
it is
sometimes
after. Okay, sir.
okay, I'll start once again. Don't worry. Okay.
Yes.
Okay. So now is it okay to you? Is the screen visible to everyone?
Yes, sir.
Okay, let me start over. Okay, so I'm creating a new file. So as soon as I create a new file, you will find the grid spacing is required, and if you see, this is our problem statement. Okay, so in the x direction you have 4 meters, and in the z direction you have 3 meters. Okay, so what I'm going to do is, in the x direction this will be my 4 meter, and in the z direction this will be my 3 meter. I don't want grid spacing in the y direction, so that's why I'm keeping this as 0. As far as this spacing is concerned, okay, you can have 1 meter spacing each. So this is going to solve our purpose. So if you click on this, so you will find there is a grid space of 1 meter each in the x direction, and there is a 1 meter each grid space in the y direction. If you want, you can directly take the grid spacing as 4 meters over here and 3 meters from here to here. That also you can do it. Okay, but if you feel comfortable, you can go for grid spacing as 1 meter each. Is it okay to everyone now? Any questions?
No, sir.
I hope not.
Yes, sir.
Okay. So let us quickly define the material, because the first thing what you have to do is define the material. Okay, so if you see the problem statement, so in the problem statement the value of E is given to you as 200 GPa. So 200 GPa is nothing but 200 kilonewtons per millimeter square, or else you can see 200 into 10 to the power 5 newtons per meter square. And if you see the units over here at the bottom of the SAP, it is kilonewton and meter. Okay, so this is Newton meter. So if you convert this into kilonewton meter, so this will be something like 200 into 10 to the power 6 newtons, or I should say kilonewtons per meter square. So the value of E should be 200 10 to the power 6. Is it okay? So now let me define the material. So what I'll do is, this is concrete, there is steel. I can add my different material also. Okay, so this, let us say this is material 1, and I want to have the modulus of elasticity for this material as, like I said earlier, this will be 200 into 10 to the power 6. So this is 200 E6. Rest of the things, they are not going to make much difference. Okay, so this is defined as material 1. So once I say okay, you will find material 1 will be added in the material library, wherein the modulus of elasticity is 200 into 10 to the power 6. So this is okay. So once this material definition is done, you have to define the frame sections. So if you refer the problem carefully, the frame section is basically, this is a truss member. So you have 1 member, 2nd member, 3rd member, and 4th member, and the cross section area of this is given to you as 2000, 2500, and 1300. Sorry, 3000. So 2000, 25, 2500, and 3000. So now you have to give appropriate area which is equivalent to this one. Okay, so what I can do is, I'll go to the define, I'll define the frame section. So let me delete this. Okay, okay, it won't be deleted. So let me edit this. Okay, so if I double click and say modify, so right now it is saying it is consisting of material 1. So let me change this to from steel to material 1, and this is in meters. Okay, so if you convert this to 100 millimeter square, so let me open the calculator. Okay, so if you take 200, or sorry 2000 millimeter square divided by 1000 divided by again 1000, so this comes out to be 0.02 meter square. Am I right? So 0.02 meter square can be obtained by taking the rectangular cross section of, let us say, if you go for, let us say, divided by say 0.02, so this will be 0.1 into 0.02. So what I'm trying to say over here is, if you take the width of the cross section as 0.1 multiplied by 0.02, so this is going to give you the exact cross section area. Okay, so 0.1 into 0.02. Okay, so this is the cross section area which I'm going to give as A1. Okay, so let us call this as, say, A1. Okay, A1, and it will be having the depth. Okay, so it will be having depth as 0.1 and width as 0.02. So depth will be 0.1 and this will be 0.02. Okay, so this is material 1. Let us call this as A1. So this is going to give us a cross section area which is similar to 0.02. Have you understood this? Any questions as far as this part is concerned? Okay. Yes.
Yes, sir.
Yes, sir.
Fine. So now let us define the another cross section area. So this is 2500. Okay, So 2500 meter square. So this can be calculated as say 0.1 into 0.025. Okay, so this is coming out to be 0.025 meter square. So same as this one. So if you multiply this into say 1000 multiplied by 1000, so you are going to get 2500 millimeter square area. Okay, so basically what I'm trying to say is 0.1 into 0.025, this is the cross section area. So this will be calling this as A2. So let me go to add rectangular section, and the material will be mat 1, the depth will be 0.1, and this will be 0.025. Okay, so this is your A2. Okay, so similarly now you can define A3 also. This is 3000 millimeter square. So I am directly adding one more rectangular section. So I am calling this as A3, and this is consisting of material A1. So depth will be 0.1 and 0.03. Okay, so likewise now you can have A1, A2 and A3 in your library depending on the cross section areas which are given in the problem. Then thirdly, you have to define the static load case. Okay, so in the static load case, remember one thing, this has to be converted to 0. You don't have to press OK. You have to press first the change load. Okay, otherwise it won't be accepted. So once you press the change load, this one will disappear and 0 will come into picture. So I'm saying change load. So this is 0 now, and then I'm saying OK. So this has removed the dead load case to 0. So this part is done. So now the drawing part. So now we have to draw the frame sections. So I'll go to draw and frame section. So this is my, from here to here, this is my first, then here to here, this is, sorry. So let me undo this. Okay, so I'll go to draw once again, draw the frame element. So from this grid point to this point, this is another, and this is to this another. And if you refer, there is a diagonal member also from 1 to 3. So from here to node number 3. So this I have successfully drawn. Okay, now we have to give a hinge supports in this node number 1 and node number 4. So let me select this, let me select this and say hinge, oh sorry, hinge over here. So now you see the hinge is reflected in this way. And if you see this, there is a roller support over here. So I'm selecting this, and then I'm going for a roller. Okay, so my rollers are also done. Now I have to define the member cross section. So this is member cross section number 1. So I'll select this. Okay, then I'll go for assign frame sections. So this has to be defined as A1. As soon as I select A1 and press OK, you will find the A1 is assigned to this member. At the same time, A1 is also assigned to this member here also and here also. So by default, what SAP does, the first member property which you are assigning, it will be assigned to every member. So fortunately, the member number 1 and member number 3, it is having A1. So this and this, they will be A1, this will be A2, and this will be A4. Okay, so A4 here, it is having cross section area as 3000. So in our case over here, this will be A3. So here assign frame section, this will be A3. Okay, I have given this, although I have named this as A3, but this is A4 over here. And in this vertical one, assign frame section, so this will be A2. So now you see this is A1 and A1. So this is A1 and A1 here and here, which is having 2000 millimeter square area. And this is your A2 vertical member. So A2 is having 2500 millimeter square area, and your A4 is 3000. So here also you will find this is 3000. Okay, is it clear to everyone? Okay, shall we continue? Okay, boys.
Yes, sir.
Fine.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So now what is remaining is the load. Okay, so there is a vertical load 3000 kilonewton, sorry, 300 kilonewton, not 3000, 300 kilonewton. So you see our units over here, it is kilonewtons and meter. So I am selecting this. So as soon as I select this node, this comes into picture. This icon is highlighted. So on this, I have to apply the global Z direction load. Okay, that to how much quantity? This is 300 kilonewton. So this is minus 300. Why I'm putting minus sign? Because positive Z is vertical and the load is in the downward direction. So you'll find this is 300 is acting downwards. At the same time, if you refer this picture, you will find there is a 200 kilonewton horizontal load which is acting on the roller. So I'm selecting this member, or not this member, at this joint actually, and then again I'm applying this. So here you'll find this is already there, so let me put it 0, and here I have to put the horizontal force in the global x direction. So this is your global x direction, okay, and its value is 200 kilonewtons. So I am simply putting 200 kilonewtons. Okay, once I say okay, so you'll find here 200 is printed and here 300 is also printed. So I think we have done with all the inputs which is required to solve the problem. So let me save the file. So it is asking me to save the file. So let me go to the SAP and say experiment 1. Okay, let me replace this file. Okay, so this file is now saved. So now I have to go for analyze. Before analyzing, I have to set the options. So in the set option, I have to select the space truss. Okay, so in space truss, UX, UI, UZ both are considered, but this is a 2D truss, so UZ can be also removed. Okay, even if you keep it there, it is not going to make much difference, but still, since this is a 2D truss, so UX and UZ will be there. So I'm just selecting UX and UZ and then I'm saying okay. Let me save the file one more time and then say analyze and then run. So if everything is okay, you will get the message that is analysis complete. Otherwise, you will get some error message. So once you say okay, you will find a typical deformed shape is displayed on the user screen. And now if you want to see the results, so here this is undeformed shape. Okay, here if you click, this is a deformed shape for any of the load cases. Right now there is only one load case. So let me go to undeformed shape. Here you will find there is a joint reaction. So here if you select this reaction, so you will find the reactions are displayed on the screen. Okay, so here there was a ruler, so you will find there is a vertical reaction of 261 kilonewton, here 38 kilonewton, and here it is 0.1 kilonewton. Okay, let me just zoom out a little bit. And the horizontal reactions are also displayed. And if you want to see the actual forces, so you just click on member forces. Now here the actual forces has to be selected and then press OK. Right now you will see the forces in different colors, so yellow and orange and so on. If you want to see the values, just ignore the field diagram and just say show values. So you will find the values are also displayed which are there in the truss members. Okay, then if you want, you can go to the print output tables. So print output table, if you want displacement, you can click displacement. If you want reaction, you can deform this one, and space or the member forces are also required. Okay, all this thing has to be printed in a file. So right now the file is there, sap expt and experiment1.txt. So once I press OK, the file will be stored. Okay, so let me create let me open that particular file. So this is my computer sap, and this is the latest txt file. So you'll find that the member forces are displayed over here. This is the joint displacement, so this is the dx value and this is also dx value. So this is a joint number 2 and this is joint number 4, and this is a y displacement value at joint number 4. So right now you see I have made some mistake, because of that the third node is missing, but you can see this is joint number 4. So joint number 4 is nothing but this one, and this is joint number 5 over here. Okay, so there is no joint number 3. So joint number 4 is displayed in x direction as well as in the z direction. So you'll find in the deformed shape also that the this point has moved in the x direction as well as in the y direction. As far as this part is concerned, this has moved only in the x direction, which can be clearly seen from these values. Okay, So all these values, they are in meters, okay, because everything is done in the meters. As far as reaction is concerned, you will find the reactions, the same reactions we have seen earlier on the screen. So the values of reactions are like, on the joint number 1, the vertical reaction, or rather the x direction reaction, is 148, and z direction reaction is 38. And similarly at node number 2, only vertical reaction will come into picture, and at joint number 3 you will have the x direction as well as in z direction forces over here. Okay, similarly you can see the member forces also. So you will find every member is having a force of constant. So this is almost in the 199.373 kilonewton. This is in member number 1. So this is member number 1. So if you see the values, so this is your member number 1, horizontal member number 1. So this is 199.73. The vertical member is 276. So this is, sorry, 261 vertical one. And the horizontal one, the topmost is 51. So you can see this is 51, and diagonal is having a tension of 63. So you can see this is 63.79. Okay, so in this way you have to solve the problem on the SAP. Okay, is it clear to everybody? Any questions? Please let me know. Okay. Okay, guys.
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.